crash course of IAS Chemistry Unit 1 Topic 1. So in the previous videos I covered Topic 1A, B and C. So in today's video we will be doing Topic 1B. So to start off with, we have empirical formula. So what is empirical formula? So empirical formula is the smallest whole number ratio of atoms of each element in a compound. So to calculate this empirical formula, there are two methods. So either by using the mass of elements in the compound or percentage composition of each element. So what is our first step? We have to divide the mass or the percentage composition by mass of each element by that element's respective relative atomic mass. So then we will get a number. And then we have to divide the number and by the smallest of all those numbers. So by doing this we will get the whole number ratio which they are in. So we use that ratio to write the empirical formula. So let's use an example to better explain how to do it. So in this example, mass of copper oxide is 4.28 grams. So the mass of copper is 3.43 grams. So then we can work out the mass of oxygen removed is 4.28 minus the mass of copper. So it gives us 0.85 grams of oxygen has been removed from copper oxide. So then to find the empirical formula, we have to first arrange it in an orderly fashion. So here we can write copper, then next to that oxygen, as those two are the two elements in this compound. So then after that we write the mass. So in this case we are given the mass. So we have 3.43 grams of copper. Then we have 0.85 grams of oxygen. Then after that we write the relative atomic mass below that. So then the relative atomic mass of copper and oxygen we can find using the periodic table. Then we divide the mass by the relative atomic mass. So 3.43 divided by 63.5 gives us this 0.054. Then for oxygen we do the same thing. We get 0.0531. So then we can see both numbers are pretty much the same, so we can assume the ratio is 1:1, but we'll go according to the normal method. So we divide all these numbers by the smallest of the numbers. So the smallest of the number is 0.0531. So we divide this by that, we'll get a number of approximately 1, so we can round it off to 1. And then in this one, in any case, it's exactly 1. So then the ratio is 1:1. So 1 atom of copper, 1 atom of oxygen. So the empirical formula is CuO. Next, there's another method to calculate the empirical formula. This one is using percentage composition by mass of each element in a compound. So basically how much of an element is there in each compound in terms as a percentage of that compound. So we are given in this example there is 38.4% of the compound is carbon, 4.8% is hydrogen, and 56.8% is chlorine. So this is of mass, percentage composition by mass. So then we write down the percentages in place of the mass. So in the previous one we wrote down the masses. So here we are not given the masses, instead we are given the percentages. So we write the percentages of each element. Then again we find their relative atomic masses using the periodic table. And then we divide the percentage of each element by that element's relative atomic mass. So then we'll get a number. So for carbon 3.2, hydrogen 4.8, chlorine 1.6. So then we identify the smallest number out of these three, 3.2, 4.8 or 1.6. So we can clearly see 1.6 is the smallest number. So we divide all the other ones by 1.6. So 3.2 divided by 1.6 gives us 2. 4.8 divided by 1.6 gives us 3. Then we divide 1.6 by 1.6, we get 1. So this is our ratio, 2:3:1. So there are 2 carbon atoms, 3 hydrogen atoms, and 1 chlorine atom. Then we can write the we can write the empirical formula C2H3Cl. So that's our empirical formula. Next we move on to molecular formula. So molecular formula is the actual number of atoms of an element, of each element which is present in a compound. So empirical formula was the simple whole number ratio. So but molecular formula is how many atoms are there of each element exactly in a compound. So there is no division or anything. So, for example, hydrogen peroxide has empirical formula of HO, but its molecular formula is H2O2. So this is how it actually exists. But because we simplify it using the whole number ratio, in the empirical formula we write it as HO. But molecular formula, how many atoms of each element are actually there is H2O2. So that's an example of when they are different. So to calculate the molecular formula, we have to know the empirical formula and the relative formula mass of the actual compound. So, in this example, we have to find the empirical formula and then find the molecular formula. So, here they have given us the percentage composition. So, we can find the empirical formula, and as the ratio is 1:1:2, so the empirical formula is NaCO2. So then they have given us the formula mass of the real compound is 134 grams per mole. They have given us that. So then what do we need to do? We have to find the formula mass of this empirical formula. So we have to find the mass of this empirical formula. So we can use the periodic table. So one Na atom, one carbon atom, and two oxygen atoms. So then we can add their masses up to give us 67 as the mass of this empirical formula. Then we divide the actual molar mass by the empirical formula mass, and so 134 divided by 67 gives us 2. So the molecular formula is 2 times the empirical formula. So to write the molecular formula is 2 times NaCO2. So 2 Na atoms, 2 carbon atoms, and 4 oxygen atoms. So that's our molecular formula. Next we move on to the ideal gas equation. So the ideal gas equation is PV equals nRT. So the terms and the units are, so P is the pressure, and we also have to keep in mind the units are very important if you want to use this equation. So P pressure should be given in pascals always. V is the volume of the gas, which should always be given in meter cube. And then N is the amount of substance in moles of the gas, that should be always given in moles. And then R is a gas constant, so we don't have to worry about this value. So they will give us the value in the data booklet. It's 8.31 joules per mole per Kelvin. So then T is the temperature, and temperature has to be in Kelvins, not degrees Celsius, if you want to use it in this equation. So we can use this equation for gases or like volatile liquids which can easily vaporize, which are above their boiling point. And since the units are very important, it's very useful to know how to convert the units. So if they are given the pressure in kilopascals, to convert to pascals we multiply it by 1000 or 10 to the power 3, and then to convert centimeter cubes to meter cubes, the volume, we divide by 10 to the power 6 or multiply it by 10 to the power minus 6. And then to convert decimeter cube, another measure of another unit of volume, to convert that to the meter cube, which is our required unit, we divide decimeter cubes by 1000. And then to convert Celsius, degrees Celsius to Kelvin, we simply add 273. So that will give us the temperature in Kelvin. Next, we'll do an example calculation for ideal gas equation. So in this example, they're asking us to calculate the molar mass of the gas. So they have told us the gas of mass 0.28 grams has this much volume, measured at a pressure of 120 kilopascals and temperature of 70 degrees Celsius. Calculate the molar mass of the gas. So to calculate the molar mass, we can, using these data and the PV equals nRT equation, we can find N which is the number of moles of the gas. So we first step is to write down all the data we have. So we can write P is 120 kilopascals. So we have to convert the units, otherwise we can't use it in the equation. So we convert the units to pascals, and then V given in centimeter cube, we have to convert it to meter cube. Temperature is given in Celsius, we have to convert it to Kelvin, and R we can use the data booklet and find the value. And so then we just have to rearrange the PV equals nRT equation to give us N. So then if we rearrange it, we will get N equals PV over RT. Then all we have to do is just substitute the values. So then we substitute P in the units we need, pascals, meter cube, Kelvin. So we substitute them in the correct units. Then we will get this answer in moles. So this much moles of the gas we have. So then to find the molar mass of that gas, we rearrange the mole equation. So if we rearrange it to give us the molar mass equals mass over amount in moles. So we know the mass they have given us 0.28 grams divided by moles. Moles we just found using the ideal gas equation. So we divide mass by mole, we get 114 grams per mole as the molar mass of the gas. Right, that's it for topic 1D. We'll see you next time when we do topic 1E.